thank you everyone for joining. We are Deep Learning Sessions Portugal, a group of volunteers dedicated to sharing insights on deep learning inside and outside of Portugal. Today we are going to have a 45-minute talk with 10-15 minutes dedicated to questions. The talk will be given by Tiago Gonçalves. Tiago received his master's degree in Biomedical Engineering from Faculdade de Engenharia da Universidade de Porto in 2019, where he is currently a PhD student. Tiago is also a research assistant at INESC within the Visual Computing and Machine Learning Intelligence Group, and today he will talk about attention mechanisms for medical sciences.
Okay, thank you once again to Deep Learning Sessions Portugal and also to Neurospace for supporting the event. Thank you for being here. So my talk is titled Attention Mechanisms for Medical Applications, Claims, Potentialities and Future Challenges. And in the end, I really hope to have a broad discussion on the topic, because as it's stated in the title, we are going to make some claims that try to fight other claims available in the literature. Okay, so it's thought-provoking, but in the end, that's really the point of this work. Okay, so in the next 45 minutes, I will be talking about three main topics. The first one, obviously, why is this a problem, or if this is even a problem. Perhaps you can let me know in the end. And then I will give you a little bit of an overview about attention mechanisms and why we may not need attention. Let's see in the end how it goes. And finally, I will talk about the work per se. So the survey that we did on our group, where we tried to study attention mechanisms for medical applications and check if we are moving towards better or worse algorithms. So, going to the start, why is this a problem? As we all know, and that's why we are here, deep learning has been challenging human performance all over the place. Why? It's not only because we have better algorithms or, let's say, rocket science algorithms, but it is also because we have more computational power, more computers, more GPUs, and so it's easier and faster to train big models. On the other hand, we also see with this, let's say, increased access to data, we see that these algorithms are actually challenging human performance. It's quite normal to see in papers normally that some authors also state that their algorithms actually surpassed humans. That's something that I personally not agree, and then we can discuss it later. But let's just say that algorithms are indeed challenging human performance. Nevertheless, in some occasions, in some domains, these algorithms work as black boxes, which means that I have data, I have a model with millions of parameters, I feed the model with data, and the model gives me an output, a prediction. In some cases, medical one is a really good case of why it is a problem. The model isn't able to justify their outputs, their decisions. Let's call it decisions, but in the end they are just outputs. It's up to the human to decide. But so the model outputs this, but we have no idea why we provide an image, and then in the end the model said it has cancer, for instance. So this problem motivated the creation of explainable AI. So explainable AI intends to promote towards more transparent machine learning and artificial intelligence. Just one thing, in this talk I will be focusing this field of explainable AI on deep learning, okay? So just for you to bear in mind that there are several other topics of explainable AI that we could discuss, but here I will try to provide on deep learning models. For you to know, this is also a trendy topic. As you can see, DARPA is actually getting and providing huge amounts of money to researchers to study more and more, let's say, algorithms that aim to improve the quality of our models. And this topic usually focuses on three things: pre, in, and post. So what we call pre methods are the ones that focus on exploratory data analysis. Okay, we look at the data, and before even training the models, we try to extract meaningful features or meaningful statistics that will help us during the training of our models, that will help us, let's say, to audit the outputs of the model. Then we have the in-model approaches, in which we try to design the algorithms in such a way that in the end, for the end user, it's clear why the model is providing like a 0 or 1 in output. Okay, we can, if you know about deep learning, you can think about regularization methods, applying some type of constraints in the model during training, better loss functions, you name it. And in the end, perhaps the most popular one, post-model methods. And these ones are currently popular because we have the model, we already trained the model, we have data, and then we can use another box, another black box, to generate some kind of explanations. And usually these kind of explanations are based on heat maps in an image. So you have an image, you predict that it has some kind of cancer or not, and then the model actually creates these types of algorithms actually create some kind of, let's say, regions of the image that, okay, I use these pixels to output this thing. Now, as I was saying, and since we focused on these post-model methods, and why? Because we already have the models trained, and also because there is a belief in the community that sometimes there are hidden patterns in the data that human beings or domain or people from that, let's say, knowledge domains cannot extract. So we actually believe that these deep neural networks actually can extract some hidden things. The development on post-model methods, it's the most popular now, let's call it. However, we have some drawbacks, okay? As I was saying, even if these explanations make sense, these post-model methods are another black box, okay? So we use a model to try to explain another model. And in the end, what happens is that instead of having like a real explanation, we end up with an approximation. And in some cases, this may not be the best thing for us. Also, explanations may not provide enough detail. So if you work on computer vision, an image is composed of a bunch of pixels. And if we highlight some of the spaces of the image, some of the regions, perhaps we will not it will not be clear for us. So it's not detailed, it may be fuzzy. We can have like clusters of heat maps in the image. And so in the end, even if we have that, let's say, visual support, we will not understand what the model is actually doing inside. So what we advocate, and it's also my personal opinion, that we should focus on this. We should try to do more pre-model interpretability, as I was saying, more exploratory data analysis, getting to know the data in a better way, in a clear way. And also, if we are designing new deep learning architectures, we should focus on in-model interpretability. So to be sure that in the end, our neural network respects some kind of constraints related to the domain. Let's say in medical domains, we have some kind of rules that we have to respect because we already know, because the clinical community already knows that are some rules that actually apply, or they have verified that empirically this happens. So we should try to, let's say, integrate this knowledge into the design and training of our models. At least that's what our group advocates, and we also have some people in the community that advocates towards this. Okay, now that I perhaps convince you about the importance of explainable artificial intelligence and why interpretability is the next thing in AI, let's evaluate if attention is all we need. So actually this is the title of a very famous article on natural language processing, perhaps one of the first. And these guys, they proposed what we called, what we can call attention mechanisms. So these mechanisms actually derive from psychology, okay? The human beings, every time we are evaluating some kind of event, some kind of a situation, we tend to focus on specific things. For instance, I'm watching the audience and my brain is focusing on your faces, on the light. So even if I have the broader view of this image that is the audience in front of me, usually I will try to focus on specific details. And these people who actually started working on this, they find out that in problems related to, let's say, spatial temporal dependencies, this could actually work. So that's why in natural language processing, these so-called attention mechanisms were actually very relevant and actually worked. We already have lots and lots of literature on that. I will leave you with this paper in the end. You can check it. And regarding the taxonomy for an attention mechanism, we can, let's say, divide this in four levels. So we have the abstraction levels. If you have only one level or multi-level, this relates deeply to the features we aim to learn. Then the positions, so we can try, if we have, let's say, a sequence, you can try to focus on a specific part of the sequence. You can to look at let's say, the entire sequence. We can relax the problem or not. And then we can also check the number of presentations, once again, related to the features. If we only want to, let's say, encode the data in a single representation, or try to encode it on multiple representations, or even go beyond and try to evaluate multiple dimensions. And last but not least, obviously on a number of sequences, and this relates deeply. For instance, we can try to have an input, and we can try to, let's say, copy that input on the output, or try to learn from that same input their parts which are important or not, and on that we would be, let's say, living on the self-attention thing, which is actually the fuel that is powering transformers nowadays. So transformers are really good at learning from this mechanism. And in the end, we can also go to co-attention when we have more another module, or distinctive attention, and then you name it. So I will leave you these names to search later, because I'm not from the natural language processing side, but just to let you know that this actually inspired the computer vision community in the end. So a typical mechanism of attention looks like that. As I was saying, we have an input sequence, we try to encode it into a representation, and then in the end we try to learn some kind of context that will allow us to decode it later. So if we are trying, for instance, to generate some kind of text, the analogy or the intuition behind is that we have a word, and when generating text, what the model is doing is that it's trying to predict the next word, the next most probable word. And to learn this, what we want to learn is this matrix, or which we call attention matrix. So actually an attention mechanism is actually a bunch of weights in a matrix that will let us know, or will let us know how to, let's say, weight the paths that we should follow. So if I'm trying to predict a word, this matrix should let the model know that, okay, perhaps the most probable word next to this one is that way. And this is learned via an attention matrix. As I was saying, the popular architecture, the transformer, which actually powers lots and lots of language models nowadays, it works pretty much with this. So this, by the way, this is also based on matrix multiplication. So usually the authors state that this is why they are, let's say, faster than, for instance, densely connected layers or convolutional layers as well, because this is only matrix multiplication in the end, and we try to learn a weight matrix in between. So that's why. Obviously that this rapidly permeated to computer vision. In computer vision, we don't have that, let's say, temporal dependency, but we can try to model other things. For instance, we can try to model which regions of the image are more important, and on these we are talking about spatial attention. So if I have an image of something, and I know that, I mean, if I have an image of, let's say, mammography, and I want to detect some kind of lesion, and I know that I have a region where I have a higher probability of looking or finding that, let's say, lesion there. Perhaps I want to learn a matrix that has like more weights on that region. On the other hand, I could also learn, let's say, some kind of features, some kind of objects or filters, and on that part I could try to learn channel attention. So that's the analogy between the natural language processing, which actually has this temporal thing, this sequence dependent type of data, to an image which is a more, let's say, unstructured type of data, composed of pixels. So the intuition behind this is try to learn more meaningful representations, better features that could improve the quality of our models. In the medical domain, this is quite cool because we can benefit from both, or we could benefit from both. So as you all know, in the medical domain we have medical imaging, lots and lots of scanners and sensors to analyze the human body. We can talk about computed tomography, magnetic resonance imaging, positron emission tomography, and at the same time we also have text, because the clinical community usually has to make some reports, and these reports usually relate to the findings on those images. So we have a very, let's call it, rich data set that we can work with. And ideally, these will be multimodal, so for the same, let's say, individual, we could have like images, lots of reports, lots of findings, diagnosis, so lots of data. And that's why you could try to, let's say, benefit from both the natural language processing side and the computer vision side, as I said before. Obviously, regarding transformers, and I will just say this because it's quite important, we also have already transformers for vision, okay? So this knowledge from the self-attention, the dot product attention, permeated already for images with some tweaks on engineering, but it's already here. And so if you analyze some papers from the last years, let's call it from 2018 until now, we can see that attention mechanisms are actually playing a role between these three areas. But we could actually switch this one to the center, because medical actually is capable of benefiting from, or let's say, enjoying some kind of things from the computer vision, the language, and again, the knowledge that we have on attention mechanisms. So these are the intuitions, the claims of the literature, the way it works. What we did, and this is the third and last part of this talk, was to first we tried to research deeply or deeper the literature that we have on this topic, focus on medical applications, okay, so we have lots of research and literature on the other ones. We try to focus on medical ones and check if by using attention mechanisms we are actually improving our algorithms. And improving the algorithms has several dimensions, and I will try to discuss some of them with you in a few slides, and then it's up to you to decide or not if we are right or wrong. So what we did was, as I was saying, we performed an extensive review. It's actually a very, let's say, almost exhaustive review of the literature, and we had 4 main questions, okay? So that we tried to answer in the end of the research. The first one, since all the claims in the literature were like, okay, if you use attention, the algorithm will automatically improve. The first question was focused on that. So, will attention mechanisms automatically improve the predictive power of deep learning algorithms? for medical image applications, okay, in this use case. Some of the claims also, and we will understand that perhaps in natural language processing this is somehow true. Some of the claims in the literature, they say that attention mechanisms, since they are only based on matrix multiplication, they will reduce the complexity of models because we will reduce the number of parameters. So if we have, let's call it a convolutional layer or a densely connected layer, if we try to, let's say, simplify that into a simple matrix multiplications, we could like intuitively understand that perhaps we could reduce the number of parameters. But is this even right in computer vision? Let's see it. And then, if we are trying to focus our algorithms on some kind of important features on the images, can we actually state that they are more interpretable, they are more explainable for the end user, in this case clinicians? Because sometimes we, as I was discussing, we use these saliency maps, these heat maps methods to put some beautiful images in the paper, and then we say, okay, since we have these images, this is automatically explainable, but perhaps it's not entirely true. And then perhaps the most important questions of this research: how practical it is to design and build attention mechanisms. As I was saying, attention mechanisms have those properties. We want to learn a matrix, but when we are building the way that we want to learn this matrix of weights of attention, it's not clear. Even I mean, I believe that even after explaining the first slide 3 or 4 times, it's not very clear why that matrix is important, or how that matrix is learned, and why we call it attention. Because even for me, it's sometimes not clear why some mechanisms are called attention mechanisms. So it's very difficult to understand, to decouple these models that we are adding to the models, and to see if our models are actually getting better because of this small tweak that we did. So in our case, we tried on three different medical use cases. Okay, so the first one was on diabetic retinopathy. Okay, with this data set. It has several classes, but we reduced our problems. We reduced our problems into the binary case for the sake of, let's say, simplicity. And so we try with this one. Then we try with dermoscopic images of skin lesions, so skin cancer versus not skin cancer. And then we also tried with a radiography database, which is called MIMIC, and it has a bunch of cases, but we only use like 2 of them. So the normal versus the condition called pleural effusion. Once again, we keep the binary case for the sake of simplicity. And the reason we used 3 different databases was to see if our method was dependent or independent from the data. Because in some of the papers that we see, we don't have unlimited time, so it's quite normal. So authors use a specific database, they apply a specific algorithm, and then they publish the paper. And so we try to see if their methods were data or data independent. On top of this, so 3 use cases. We used 2 different backbone architectures. These ones are state of the art. They were not proposed by us. So we have DenseNet, which is quite known in the community, and then we have ResNet. They have some kind of differences. So in DenseNet, they connect. The layers are totally connected to each other, and this facilitates, according to the authors, the gradient flow when training the models. And in ResNet, they have this residual connection, which is pretty much like having an identity operation. So you have one thing, you have one input, you apply a processing, and then we multiply it by the identity matrix, and then you connect that same input in a, let's say, in the frontal part of your topography of the model. And we use these backbone architectures, and these are the ones, or these ones were the ones in which we connected like the attention mechanisms that I will explain later. So, 3 use cases, two backbone architectures and several attention mechanisms. The first one was one of the first proposed in the literature for computer vision. It's called the squeeze and excitation. And as you can see here in the dimensions, what we aim here is to try to learn better channel-wise features. So we have feature maps which actually have the height, width, and the number of channels of an image. Let's call it an input. We apply a global average pooling, and then we try to, let's say, collapse two of the dimensions. So we multiply, it's like a reshape of our tensor, and then we collapse like the spatial dimensions to keep the channel dimensions. And here we just apply a ReLU, and then we have a fully connected layer, and this fully connected layer, the weights learned here actually are the attention matrix that we want to learn. And then, as you can see, we apply a sigmoid once again, and we reshape the vector again. So in the end, we have the same dimension size of the input. But the important thing here is to see that if we are collapsing these two dimensions, we want to focus on the remaining one, in this case the channel one. And then let's say that was one of the first approaches, and then we tested with the other two approaches. And the next one actually one of the most popular ones as well, is the convolutional block, and this one is composed of a channel attention, pretty much similar to the one that I showed you later, and the spatial attention model, which is, instead of focusing on the channel, we focus on the spatial dimensions. So as I was saying, we have these two models, and now I will explain each of them. So the channel attention model has some differences from the squeeze and excitation layer, but if you keep with me, you'll understand. So we have feature maps. Once again, we collapse the spatial dimensions, okay, by multiplying, by reshaping the tensor, you name it. We keep the channel dimensions, and then we have two streams, one in which we apply max pooling, another one in which we apply average pooling, and then we also have an MLP to learn the attention metrics, and then we actually do an element-wise summation. In the end, some of these, let's say, intermediate steps, they are like a recipe, a magic recipe. So people actually try different things until they work. We also apply sigmoid, so we are recalling again the squeeze and excitation layer to focus on the channel features, and then we end up with a vector that focuses on the channel features again. So the recipe is quite similar to the first one. If we go to the space attention model, we want to focus on where, okay? So on the spatial parts of the image. And here, what we do is that we apply, or the authors, they apply a max pooling and the average pooling to the channel side, to the channel dimension, and they end up with a feature map or a tensor that has like the spatial dimensions, but just a single channel dimension. So we, in the end, collapsed the channels, and we kept the spatial dimensions, and here they concatenate these two. They actually pass these through a convolution, which generates more feature maps. They apply a sigmoid, so once again they apply an activation function, and from these our attention matrix will be the one that it's learned from this side to that side, okay? And the intuition here is to learn better spatial features. Obviously, if we want to, let's say, compare all the attention mechanisms, let's call it more core attention mechanisms with the state of the art, we also have to test the transformer one to be fair in our comparisons. And so we ended up training a data efficient image transformer, which derives from the vision transformer. So this is the architecture of the vision transformer. Most of these, as you can see, these are mostly of these are dot product, okay? Dot product operations, matrix multiplications, what they call self-attention. And then they also use multi-attention because they try to get several, let's say they have several heads because they try to get features from different levels of the architecture. And then this is called data efficient because they pick up this, they train a new model, smaller one, with the knowledge distillation. Okay, so it's they pick up this vision transfer model, they try to reduce the size of it, and they use knowledge distillation to have in the end a smaller model that would somehow learn the same things as the bigger one. And we decided to use this because this model is actually very, very big in terms of parameters, and therefore it would be unfair to compare it with like simple deep neural networks that have like less parameters. Although they have millions of parameters, they have less. And on top of this, we try to check the degree of interpretability. As I was saying in the beginning, nowadays this degree of, let's say, explainability is evaluated or assessed using these heat maps. Although I already said to you that perhaps they don't explain anything, we try to use this as a proxy. So the intuition was, if we use attention mechanisms versus models without attention mechanisms, the heat maps should, in the end, they should be different. So if we use an attention model, the heat map should be focused on specific places or not, and if we don't use, the heat map should be fuzzy, let's call it. And once again, to be sure that we are not, let's say, biased towards a method, we use two different methods to produce these heat maps. One of them is deep lift, and the other one is LRP. The way these methods work is pretty much the same. So what we try to do is we try to backpropagate the gradients from the output in order to the input. That's why we can, in the end, like get that heat maps, because we try to optimize the input. Just to recall, when you train a deep learning model, we try to optimize the output in order to our loss function. Okay, that's the way we actually learn the parameters. In here, we want to, let's say, create an optimal input, so we backpropagate the gradients from the output to the input, and we get an upsampled version of, let's say, the input that will maximize the prediction. So that's why we have these heat maps. So it's, once again, all of these post-hoc or post-model methods, they all work with backpropagation. Okay, it only depends from which type of variable we want to backpropagate, okay, in order to another one. So in the end, the experimental protocol looks pretty much like this. So we have 3 databases, 7 models, because we have the baseline models and the models with the attention mechanisms. So these ones with the squeeze and excitation, and where we have CBAM, it's like the convolutional block attention model. And to, let's say, do some kind of explainable AI, we have those 2 methods that I talked earlier. And we also add another feature, which is we try to check these models on low data regions. So the intuition was, okay, even if they all behave the same when we use 100% of the available data, perhaps attention-based models, they work better if we have less data, because if they are focusing on the feature that matter, they will end up work better. This was the intuition behind this low region, let's say, data approach.
Sorry.
One. So the first question that we try to answer is that, what can we say about the predictive performance of models? Okay, so intuitively, attention mechanisms, transformers, they should work better than baselines. But here we can see that sometimes baselines, they actually work better. And not only work better on like the full data regime, okay, they also can work quite well when using specific percentages of data. So at least in this data set, even when we have like less data to train the models, a simple baseline allegedly works better or the same. And this actually happens for the other data sets. So this one is an attention-based model. It's like its performance is quite low. Only the transformer actually is capable of attaining the same performance as the baseline ones. And this happens pretty much in all the data sets that we use. Okay, so in principle, it's not the problem of the data, as we stated later. So regarding this test on performance, what we know is that it's not clear why. So it's not clear, or it's not direct, that we should expect better performances in terms of accuracy when using attention-based mechanisms or transformers. And also, as I said before, if they try to learn the most relevant features of the data, they should work better in low data regions. So if I only have like 1% of the data to train my model, why the baselines actually work quite well as the attention based? For us, it doesn't make sense, because if you are using attention, they should be better, because they are learning, supposedly they are learning better features. And one of the problems in the machine learning literature, especially in conference papers, is that usually the results that, let's say, beat the state of the art, they are marginal. So sometimes we have papers when we use these, let's say, the authors use these some kind of novel attention mechanisms, and they surpass like the state of the art by 1%. It could be by chance. If you don't have like a statistical test that actually assure us that it's significant, so it could be by chance. But in the machine learning community, this is not like a big deal. Sometimes when we beat the state of the art by 0.5%, it's good as well. So we need more critical view on these results. What about the complexity, as I was saying? So in natural language processing, by using only, let's say, matrix multiplication instead of, let's say, densely connected layers or LSTMs, we can give you that. Okay, perhaps the complexity will decrease. But in computer vision, we have to bear in mind that we already have a baseline models that have a quite high number of parameters. Okay, so 7 million, 23 million, and if we are adding attention mechanisms that are actually based on densely connected layers or convolutional layers, as we saw previously, we are adding more and more parameters. So in the end, we increase the number of parameters, at least for the computer vision, let's say, task. The exception here is the data efficient transformer, and this is the reason why we use this one, because it has like 5 million by default, which is comparable with at least the DenseNet, which is let's say the smaller of the backbone models that we use. But once again, about the complexity, some of the claims that we see in the literature, they are not that right. So it's not direct that we will decrease the complexity of our models. And that gives us the next conclusion. So the first one I already talked about, so using attention mechanisms will not decrease your model complexity. Okay, it's not direct. Although by relying on simple operations such as matrix multiplications of products, they may reduce the training time of your algorithms. So we can think about convolutional neural networks. When they were introduced for computer vision, for image analysis, they actually reduced the time versus using like densely connected layers, because it's faster, and we don't need to, let's say, reshape the vectors, or in the case of densely connected, flatten the vectors past all the pixels when we use convolutional neural networks. So we understand that by using a simple mathematical operation such as multiplication, we can reduce time, but not complexity, not the number of parameters. And then, if by adding these mechanisms we are increasing the number of parameters, how can we be sure that we are getting better results, or allegedly better results, because of these, let's say, mechanisms? Or we can just ask if our models are not overfitting, because if we are increasing the number of parameters, if we have unlimited parameters, the model will behave like perfectly. So that's the nature of overfitting. So if we increase the number of parameters and keep the database as it is, we, by principle, we should overfit. So that's one of the questions that we also left in the end. Now, perhaps the most important question: what about explainability? Okay, so as I said, we use those techniques, those saliency maps, heat maps techniques as a proxy of the interpretability degree of our models. And I mean, I will invite you to give a look, like for a few seconds, and to see if by using attention or no attention, if you see some thing that is actually significant for your hand, even though you are not from the clinical community. When you try to use these, let's say, heat maps, which are in red and blue, we can see, or perhaps I'm biased, but we can see that there is no clear pattern here. So if we use attention or not, the heat maps, they don't really behave the way they intuitively they're supposed to. So if we use, in our opinion, if we use attention, these maps should be more focused, at least in some degree, and that doesn't really happen. Okay, in this use case, in the skin lesion use case as well. So sometimes with this squeeze and attention layer, the heat maps are quite similar to the no attention layer, and sometimes we have like very low activations even when using the convolutional block, so it's not clear. And in the radiograph use case as well. So once again, about explainability, that's the question is still here. So most of the papers, they say that by using attention they are increasing the explainability of models, but I mean, I guess it's not very clear after checking these images. And so we also conclude on this. So when our intuition, as I was saying, was that with attention mechanisms, the heat maps around the image should be more focused. It didn't happen, okay? And when we change a backbone like a ResNet or DenseNet, these heat maps will behave differently, which is normal because the architectures are different. But so we don't have really a clear pattern, so it's difficult for us to see, okay, this is actually interpretable because we are using this, and if using that, this is not interpretable. It's difficult. And that's another problem of this field of, let's say, of knowledge. It's still not possible, or at the moment, it's difficult to understand what is a high quality visual explanation. As I was saying, looking at those heat maps, we can start imagining things. We actually want to extract some things. Sometimes some papers, they show you that the more you look into the heat maps, the more things you can extract from them. And as I was saying, these methods of these post-model methods, they work on backpropagation, which means that I can generate the heat maps even for the wrong class. So I have a model, I know that the ground truth is like 0, and I want to generate this heat map from the 0 class, which is the ground truth one. So we can generate that. So we pick up this class and we try to optimize the input to obtain the heat map, but I can do the other way around. I can generate this heat map for the wrong class. And we actually, in the original paper, we have examples of like heat maps for the wrong class when we change the class and try to generate the heat map with that image as well. And the pattern is simply not clear, okay? Visually is simply not clear. So it's difficult to state, like some authors do, that by using attention mechanisms, at least for computer vision, we are learning the right correlations, okay? We know that deep learning algorithms are really good at learning correlations, the so-called hidden feature that we tend to believe exist, but perhaps we should be careful when learning this narrative. And then the final question, and the one that I want to discuss you in the end of the presentation, is are we actually moving towards better algorithms, at least for medical applications? So we see regarding performance and complexity that, I mean, with attention they are more complex because they are more parameters. Regarding performance, they perform the same way, so there is no like significant change in the accuracy of the models. When you try to use a method to generate heat maps to understand if we increase the explainability or not, the patterns of heat maps with or without attention, they actually don't have a pattern, so it's difficult to understand if they are more interpretable or not, at least in the visual way, in that proxy that we are using. However, community is moving towards the use of these algorithms, so they are using these frameworks, and they argue in the papers that they are actually increasing the quality, the transparency, and interpretability of deep learning solely by using these frameworks and by integrating these frameworks. However, I hope that I showed in this presentation and in the paper that this might be not entirely true. Okay. However, this paper is not only about criticizing and, let's say, and destroying the claims of others. We feel that we have future challenges or new hopes for, at least for attention in the medical domain. So even if the community is like going through the use of attention mechanisms, we should start by thinking about them as something that should increase interpretability. So perhaps we should pick them and try to see, okay, what are the features of these mechanisms that we can tweak to achieve in the end a box that is clear, okay, that a box that I can audit, that I can go there and see, okay, if I change this, I know the behavior of the model. On the design and integration, we believe that we have a big path and a big, let's say, road to walk, because some of these mechanisms in the papers, in the original papers, they are presented along a specific backbone. For instance, in the squeeze and excitation mechanisms that I showed previously, they use ResNet 50, okay? And they only try, on the paper, they only base all the results on this mechanism along ResNet 50. And when we try to integrate this module on a DenseNet, which has a different architecture, it's not clear where in the architecture of the DenseNet, okay, the topography as we call it, where should we put the model? Okay, so if we imagine deep learning model as Lego pieces, it's difficult to know where we should put like the attention piece on the construction. And so this is a problem. So it's important for us to try to get to some kind of, let's say, generic framework which can, let's say, guide machine learning or data scientists into, okay, you should try to put your mechanism around here in the architecture, because it will be more prone to these or those features. Because in our case, everything was very, very empirical. So we tried to mimic the way they did with ResNet to DenseNet, but the architecture is quite different. Nowadays we are assisting to the rise of transformers, so they are here, they are creating some kind of revolution in the, let's say, language models. We have ChatGPT, we have all of this is powered by transformers, and in imaging as well. So although I believe, and we believe, that there is some kind of hype on these structures, solely because they work only with matched multiplications, they are more simple, and they actually work a lot when we have a huge data set. We, at least in this use case, in the medical domain or in other domains that may impact our lives, okay, we can keep on this, they are powerful, it's cool, but we try to see if they are interpretable or not, because for, at least in the medical domain, I don't care if I have a transformer that actually predicts cancer with 100% accuracy, but in the end, it is not capable of explaining the functioning, the inner function that actually led the calculations into, okay, it's cancer. And last but not least, the wrap up all of these things, we should increase the way we actually assess interpretability in the algorithm. So in this paper, it's one of the flaws. We used visual heat maps to try to understand the quality of interpretability of these models, but perhaps we should try to move on into another domain. Perhaps pixel or creating heat maps on pixels maybe not enough. It's important that we could hopefully try to convert what we know from the image into meaningful knowledge that the end user, let's call it a doctor or a clinician, can actually compare. This makes sense. And that's it for today. I'm now open for your difficult questions if there are so. And again, I will share you all these things with the community. And once again, thanks for this learning session, Portugal, for inviting me, and Aerospace for providing the room. And thank you for being here. I hope that I was clear and that the presentation was cool enough. And I hope that I didn't took too much time.
So we will now open the questions part to the audience, if anyone wants to ask something. I have a couple of questions on my own, but maybe we can start with the rest of the members.
I could ask one or two. I'm curious, when you're testing or trying to compare different architectures, like you did here, how can you be confident in your findings? Because maybe some of the models were worse than others, because maybe you didn't optimize as well the learning regimen. How can you, what steps do you take to be more confident that that's the close to the peak performance of the architecture for that process?
We actually, we try to not damage a lot the level of hyperparameters that we have in the experiments, but we actually optimize some of the hyperparameters to attain the best performance that we could get. So in some databases, the performance that we describe are actually similar to the ones described in the literature. So we use that description of the literature to say, we are not very far, we are similar, so the model should be training well. But that's a very good question, because sometimes when we are trying to optimize some models that are from other papers and they don't work, it's difficult to know if it's our fault or if it's not reported in the paper. But we try to optimize everything, and in the end we try to use those optimal hyperparameters that we find out to train the models. Although this was very empirical, so sometimes we tweak one or another. Perhaps there are better hyperparameters that we can use, but that's one of the limitations of the study.
Good, thanks. I had another one. I never worked seriously with explainability parts, but you were explaining well the problems with how to evaluate if explainability is good. And looking at the images, I wonder if it's possible to create some sort of benchmark where you annotate in the image where the main problem is, and then you compare the heat map, if it overlaps well. I don't know if there are methods like that to...
You have a point, yes. In some cases, so I didn't actually reveal everything, so in some medical domains, these heat maps, they make sense, although, I tend to criticize these heat maps because, as I was saying, if I give you a paper with a heat map and you want to find out something, it's usually inexplainable. In AI, authors, they really want to convince you that they find out something. So if you look at the heat map for an hour or two, you start to there is something on this heat map that actually convinces me that the model is on the best, is going or behaving the best. But in radiography, for instance, I have a friend who worked on that. For radiologists, The heat map based explanations, they are very cool. So we have a work on a different topic in which my colleague he generated these heat maps in radiology, and he used these heat maps to feedback the models, so to improve the training. And for radiologists, those are good explanations and those make sense.
Mm-hmm.
So perhaps on that domain, we could actually create some kind of annotations, let's say more fuzzy, not that strict, but that could be a proxy to the quality of the heat maps. So yeah, in some domains, these heat maps may make sense. Okay, it's not like they are garbage. They can be useful for some things, but we argue that perhaps we could go the other way around and try to impose interpretability by design in the model.
Mm-hmm.
But it's a difficult path.
Part of the explainability of the KPIs for explainability, for example, in this domain, is if a clinician can, for example, from the heat map, can derive reason why the heat map is like that. I would say that that's a KPI. If a clinician looks and say, this heat map makes sense. I was wondering if it's possible to use the heat map, like do the opposite route. Use the heat map to train the model.
Yeah.
For example, if I track a clinician doing an exam on an image, I could compare the generated heat map with the eye tracking results, for example. And we could learn heat maps and therefore the attention matrix. Is that an option? Is that viable?
Yeah,
it's a lot of work, but
yeah, that's my first point is that like human studies are. I mean, for a person who works in explainability, I should be doing human studies all the time, but we don't have time for that, and the PhD only lasts like 4 years, so. But yeah, that would be preferable. So we could like derive ground truth heat map explanation. The work that I was talking about, my colleague, he did the other way around. So you have a model, you train the model, and then you can generate heat maps after training. Okay, so you can generate all heat maps for all the data set. And my colleague actually used these heat maps during training along with the image. So we have an image, you concatenate the heat maps. I guess it was the concatenation or a multiplication, but you somehow mix the heat maps with the image, your input, and then you feed again to the model that you want to train. And my colleague like verified that when you use these heat maps, even if they are fuzzy, at least in the radiological domain, they actually improve the performance of models. And for radiologists, using these outputs, it makes sense because for them, those visual explanations, they were okay. So for them, it was the best case scenario, and they accepted. So one of the things about interpretability is that if they respect the constraints of the domain, it's okay. So if for a person of let's say skin lesion or domain, those explanations are okay. For us as machine learning practitioners, that would be fine. The problem is that when we do papers, we usually don't ask the domain about the quality of these explanations. And why? Because once again, it takes lots of time, and to be fair, we lose competition to the other people. So no one is doing this in the community. The ones who actually do human studies, which in my vision they are the best. So the complete studies, they would be preferable. But if you want to compete like in top conferences or so, you lost time. It's basically as that. Although human studies would be preferable, obviously.
you said you wanted to move away, not you, but it would be a good idea to move away a little bit from heat maps. Which other outputs would yield explainability to a clinician?
Yeah, so one of the things that I believe that we can do is that we can first we should try to use more data. So instead of using like I have an image and I have the label. So usually what we do in medical imaging is that we have an image. I know that this is cancer or not, and then we train models like that. perhaps this is not even correct, because I mean, these heat maps actually, in some of the papers, they pointed out to other properties of the image that were not like correlated with the diagnosis, for instance, the date. So you have papers which show, actually, so the community started to criticize heat maps because they showed some things that were not making, that were not making any sense. And one of the things was that, so I have a paper, I don't have, it's like from other authors, but they show that they use like this heat map generation model, and then for cancer, the model was trying to look at the dates, because some images, they have the dates there. But a good explanation, so let's say, a more meaningful one would be, for instance, if we train the model with more data, clinical data, we could try to regularize the model. We could try, for instance, to learn some kind of feature vectors that correlate, for instance, with, I don't know, in skin lesion you have other features like the size of the lesion, the symmetry of the lesion, and we could try to impose that learning on the feature maps of architecture, and then we could try to use, let's say, another model, I don't know how and if we should even do it, but another model that could actually like analyze the mechanism of our deep architecture and say, okay, this output is like this because your feature vector correlates with this symmetry, and this symmetry by rule, like points towards that diagnosis. And there are some people that are already teaching deep learning algorithms how to learn these rules. The biggest problem here is that these problems are actually harder to optimize versus like training a model that receives an image and outputs some things. But there are actually like some rule-based models on the literature, but they are quite hard to learn. You need lots of time and mathematical background as well to like solve that difficult optimization problem. But that would be preferable. If you could like extract some causal like relations from an image, from the pixels, which I don't know if we can or not. It's Holy Grail in causality nowadays. But if we are able to extract causal relations from the pixels, it's a Nobel Prize. So you pretty much solve the problem in terms of interpretability, of course.
So I also have a couple of questions. One of them is, you've showed a table that compared attention models and their number of parameters, right?
Yes.
But arguably, from an application standpoint, it's also super important to have inference time, right?
Yeah.
So my question is, how does the attention mechanism in the model affect the forward pass, the time of the forward pass of the model, right? And do we also have data on that?
Yeah. So basically, you are talking about the flops, right?
Exactly.
So that's a very good question, because we actually didn't do it when we published the paper, but it would be interesting to do it. However, my intuition would be that at least in this set of models, so the ones that actually use convolutional neural network backbone, as soon as we increase the number of parameters, I would say that they should be like the opposite of faster, which is the word that I'm forgetting. But in the case of transformer, this guy is quite fast. So the transformers, they actually won. I would say, at least by experience, they won on the inference time. So that's why the number of parameters may actually increase, but we have this note on that. Okay, perhaps they can improve the inference time, although we don't have experiments for the ones based on the convolutional backbones. But since those attention mechanisms for computer vision, they are actually made of some kind of convolutional and densely connected layers, as we saw, I would say that the inference time would increase, at least by a bit.
Okay, thank you. And another one, it's not a technical question per se. It's more related to something that you said at the beginning, which was that some authors overclaim that deep learning algorithms are surpassing human doctors in diagnosis.
Yeah.
And I was wondering if you can elaborate a little bit on that. On this.
Yeah. So I started thinking about this after some discussions with the previous guy that was here in deep learning sessions with you, because he had an important argument on why we shouldn't like state that in papers. Because when we state that our models are surpassing humans, we also have to bear in mind that perhaps, so we have two ways. Or the data that we are using to train is not well annotated, and so humans, in the end, they were wrong annotating the data, so our models perhaps by chance they could be learning better because they are failing on the annotations. And we also have some works in the group that they verify that. So we sometimes we have some colleagues that they work like deeply with clinicians and they train a model, they generate the predictions, and then they send the predictions back to doctors, and doctors in the end they change the annotation. So this is one point. At the same time, in papers, when they state this, they don't say which group of humans actually they use to assess. So I can be training a model on a specific data set that was annotated by a specific set of humans, and it's not really fair to, let's say, use another set of humans to test the predictions and their annotation, because even among humans the annotations they may like differ a little bit. Okay, so even the data sets that we have, they are not like well curated, well verified. Like we should have better data with more coherent annotations. Once again, it's a matter of time. So that's why I started to think about that, and I started to, let's say, refrain from using surpassing human performance. Although in the first slide I have a paper from Google, that one on mammography, and they stated that like they are surpassing, but they actually did a human study with the same people that they used to annotate the data. So in the end, it was the people from the same cohort, and the model was quite getting like similar results. Although they don't state like strictly that their model is actually better than humans, because if the models are learning from humans, it's quite difficult to see why should a model like be better. But that's a philosophical point of view, obviously. So.
Okay. So if
I have some questions as well. Sorry. So the backbones are you using pre-trained models, or are they trained from scratch?
Yeah. So we initialize the parameters from INESC.
Okay. And when you add the attention modules in the CNNs, how is that initialized? Is it random?
Okay. Yeah. So we initialize all the remaining parameters of the models from ImageNet, and then when we add the attention mechanisms, they are randomly initialized, basically. That is also a flaw. We could try to train the models first on ImageNet, have better initialization parameters, and then test it.
Yeah, because I was thinking that could also be one of the reasons why the models with the attention modules are performing worse, because the other layers are used to not having that on the pre-training. So
yeah, that's a fairly good point. Yeah. We didn't do that, and the reason why once again the reason is always the same. So the time to train on ImageNet, but I mean we could do that, of course. That's a fairly good point. And the other thing is that related to the third problem, which is like how to integrate an attention mechanism, which you could see as a piece of a puzzle. How should we integrate that in the architecture of models? Should we put it between the residual layers? Should we put it between the densely connected layers in the case of DenseNet? I mean, I don't know. Everything I did was empirically, and even the authors in the papers, they don't really explain why they put the attention mechanisms there.
For you said that in the squeeze and X citation paper they show results for the ResNet, right?
Yeah. So
do
these,
they have a pre-trained model also with that?
yes.
So that block could maybe
They have. So I
something to.
I should check the code. I don't know. Yeah, they have the weights available actually.
Okay.
I don't know if we did the other way around just to not be biased towards this. However, they actually have the weights, and I don't recall if we used the weights or if we on purpose if we didn't. But these ones they have. Yeah, since they use this backbone, they trained all from scratch. In the other architectures, the CBAM, for instance, they don't really have the. I don't even recall if they have the code or if we had to like implement it from scratch. But sometimes it's difficult to reproduce the work.
Yeah. And another question, when you show the heat maps, those are only for the CNN-based models. Is that because those algorithms are specific to CNNs? So you don't show the transformer?
Sorry, I have the heat maps for the transformer. Perhaps I was not clear. So, okay, in the case of transformer, we had to use like a,
okay.
Yeah, it's here. It's not very clear. And actually, in the case of transformer, the heat map is quite focused. Okay, but here we had to use like a framework which is based on the LRP, but only for transformers. We actually got lucky because even these, let's say, backpropagation frameworks, they are not easy to implement from scratch. Fortunately, PyTorch has an API which is called Captain that already has some of these algorithms implemented by us. So as I was saying, it's the same as optimizing a model. Instead of using the loss function, we use the output with respect to the input. And when we optimize the model, we use the loss function with respect to the weights of the model, basically. And for transformer, we have this implementation that was created by another author, and we use this on top of it. So, by the way, even for the heat maps, these visualizations that we have, they are tweaked, okay? Because these gradients, they have a range, and to produce these visual, let's say, images, we have sometimes to limit the range, which may influence the way we see things. That's why it's troublesome to use something that humans will only assess by visualization, because once again, even by tweaking the limits of the values of these pixels that we have, of these activations, we could like be influencing the output of the explanations. But yeah, this was an implementation that we used from another author. By the way, our code is publicly available in the paper, so if you feel that you want to criticize or audit or tweak some things, I invite you to go there, leave a star please, and use it, because we try to put everything available for the community, so you guys could actually go there and see if I'm wrong or if we were wrong during our experiments. It can be one of the reasons why we ended up getting these conclusions. We don't know.
Okay, thank you.
Is it common in when doing these tasks in radiology to do transfer learning, from like something trained on ImageNet? Is it? So that same colleague of mine who actually worked on the using the heat maps to train to let's say give feedback to the model training. When we were working together on that topic, we empirically once again we detected one thing. Sometimes it's better to initialize, at least for some medical applications, it's better, for instance, to initialize your models with the weights pre-trained on ImageNet than to initialize, for instance, on the same task from a medical domain. So basically, long story short, if I train a model on a radiology data set and then I use these weights to train on another radiology data set, perhaps the model which is pre-trained on ImageNet will attain better performance. And we still don't know why. We believe that it's some kind of domain generalization, that it's maybe inherent to
these algorithms, but these are only fancy words. We don't really know why. I mean, if in ImageNet we have millions of images, we end up learning more general filters than when trying to learn solely on a use case and then changing the domain, but not the use case. But the images ended up being different, but we don't really know why this happens. So yeah, it's usually, even for medical, we initialize the models on ImageNet, and that's okay.
Okay.
By curiosity, how are things done in the industry?
In the industry,
Do you know?
I mean, I know some cases. I was in Web Summit last year, and we discussed some with some people from the industry regarding these medical use cases, and then we start to ask things. So basically, they tend to overfit their models, and they assure that their models work really well on their images. So if you ask some person in the industry if the model will work like well on a different images acquired from a different sensor, they can say that they will work, but you can see from their eyes that perhaps they will not work that well.
So they throw a lot of money.
Yeah, I mean, because this domain generalization part is not easy to optimize. So
They can fail.
it's difficult. The best way is like to implement some kind of continuous learning pipeline. So you have a domain, and then you keep feeding the model with images from other sensors, and then you expect that in the end, since you have like millions of cases, you learn the right correlations. But perhaps you should use better clinical data, not only images. That's my point. I may be biased.
So if there are no further questions, I'd just like to thank Tiago and the audience for attending, and I'd also like to inform that the video will be available on YouTube as well as all the other resources, and I would like to ask you to fill a feedback form that is available on the meetup description of this event. And if anyone in the audience is interested in presenting their own work, we also have a speaker application link in our website. Thank you.
Thank you.